Khalid? Okay, we on the air? I guess? Not yet?
Oh yeah, go ahead.
We are. Okay, are there any questions? So apparently a few people still don't believe me in the Monty Hall problem. I'll try and discuss it a little bit more today if we have time. But otherwise, if you don't believe it, the only thing to do is to simulate it. So write a computer program that simply has the contestant first pick a curtain at random, and of course 1/3 of the time he will pick the curtain that has the car, and then have Monty well, I guess the thing to do is have Monty then pick a remaining curtain, one of the other two curtains. Now, in the case in which Monty knows what's going on, then any time that Monty in your simulation picks a car, just throw that out because that's never going to happen. So just ignore those possibilities. That is, imagine that when Monty picks a car, that experiment had not actually been performed. So Monty will always pick a goat, and then take the ratio of the number of times that the contestant would win if he were to switch from his original choice to the remaining curtain. And if you do that, I'm sure you will find that the fraction of time the contestant would win by switching is 2/3. Okay, the reason being that the probability is 1/3 that the contestant will originally pick the car. And if Monty never picks, always shows you a goat, then what that means is that knowing that Monty is always going to show you a goat means that when he does show you a goat, no information has changed, no new information has been given. So if the contestant originally had a probability of 1/3 of picking a car, then when he switches, the chance that he will switch away from the car is 1. So therefore, if he picked the car originally, which happens with probability 1/3, he will lose when he switches. And if it did not pick the car originally, which happens with probability 2/3, then he will win when he switches. So if Monty always shows a goat, therefore, if that's the fact, then the contestant will win 2/3 of the time by switching and 1/3 of the time by staying. Now, I'm saying that. You may not believe it. The only thing to do is either to follow my analysis or come up with a better analysis, or write the simulation, because I think if you simulate it, then you'll see that's the way it has to be. Okay.
I got a small question.
Yes.
By switching, what do you mean? But if you switch, you're going to take the Monty's curtain or the remaining curtain?
No, there's only the remaining curtain. There are 3 curtains to start with. The contestant picks a curtain. Monty picks another curtain, so that's 1 curtain left. If the contestant has picked a car, which happens 1/3 of the time, then when he switches, he will lose. If the contestant did not pick the car, which happens 2/3 of the time, then when he switches, he will win, because Monty has eliminated the other goat, so he can only switch to a car. So therefore, knowing that Monty is always going to show you a goat doesn't tell you anything in a probability sense. What it means is that if Monty always shows you a goat, then the contestant will win 2/3 of the time by switching and 1/3 of the time by staying. Because 1/3 of the time, he will already have picked the car, so if he switches away from it. And 2/3 of the time, he will have picked the goat, and if he switches, he must switch to the car because Monty has removed the other goat. Okay? So that's the intuitive argument. Now, intuitive arguments are, by their very nature, are not rigorous, so they could be wrong, and that's what the purpose of the mathematics is to show you that, in this case, that intuitive argument works. The intuitive argument that leads to 50-50 That, of course, is also an intuitive argument, but the mathematics doesn't support that, so that argument is wrong. Now, today, I think, if I get to it, and if I don't screw up, I'll make another argument that maybe should convince you that the contestant should always switch, because if Monty shows the goat by chance, the contestant doesn't lose anything by switching because his chances are 50-50. But if Monty shows you a goat on purpose because he knows where the car is and never shows the car, then the contestant's probability of winning will go from 1/3 to 2/3, or in other words, he will double his chances of winning by switching. Okay, so where we are is we're talking about now the next topic. Here we are. We're talking about section 3.3, the law of total probability. So this is a continuation. We're still talking about conditional probability. In the law of total probability, there are several versions of it, and the version that I want to use is on page 96. I don't really know why the author gave these versions. One would have been enough. But it's theorem 3.5. So it's theorem 3.5, page 96. And what he says is this. Suppose that you have a sample space, and the sample space has a partition. Now, the word partition, there's a definition given in the book. Let me tell you what page that definition is on. I think it's on page 95. It's on page 93. So here's the definition on page 93. So you imagine that the sample space has a partition, which means that there are events, call them B1, B2, B3, and so forth. The reason that the author has various versions of this is, first he does it for the case where the partition has only 2 events. Then he does it for the case where the partition has n, a finite number of events. Then he does it for the case where the partition has an infinite number of events, which of course you can't draw. But the infinite number of events seems to me to cover everything, so just look at that, it's no big deal. So the idea is that the sample space S is like a jigsaw puzzle. So there's event B1 and B2 and so forth. And these events cover, that is, their union is the whole sample space. And furthermore, that's the first property. The second property is that the intersection of any pair of them is empty. So the intersection of Bi with Bj is empty as long as I does not equal j. 2 different. So this is like a jigsaw puzzle. So when an experiment is performed, some event occurs, some point happens. And based on this, that means that one and exactly one of these B's must occur. Now, suppose that in this sample space, there's some other event A. So here's just an arbitrary A. And the question is, I want to find the probability of A. And the formula says, the way you do that, one way to do that, if you have such a partition. Now remember, this looks abstract at the moment, but when I give examples, you'll see that this partition idea is straightforward. Okay, so it says the probability of A is, first of all, the probability of B1 multiplied by the probability of A given B1, plus the probability of B2 multiplied by the probability of A given B2, and so forth. So I'll prove this more or less, but this is intuitively obvious if you think about it. Because if you use the frequency interpretation of probability, what this says is, I'm going to perform this experiment, and I want to know the fraction of time that when I perform the experiment, I'm going to get a point in A. And this says, well, I know that when I perform the experiment, I must get a point that's either in B1 or B2 or B3 or B4 and so forth, because those B's are a partition of the sample space. Now, therefore, the fraction of time I get A is, first of all, the fraction of time I get B1 multiplied by the fraction of time I get A if I got B1. That's what conditional probability means. Plus the fraction of time I got B2 multiplied by the fraction of time I got A if I got B2, and so on. Now, a more formal proof goes something like this. Let's see. You can say that since S, the whole space, is the union of these guys, you could say that A is equal to the intersection of A with S, which is therefore equal to the intersection of A with B1 or B2 or B3 and so forth. And now you could say that since the B's are disjoint, then this is the same thing as the intersection of A with B1 and the union of that, of the intersection of A with B2 and so forth. So this piece right here, let's go back over here to this diagram. Here is the intersection of A with B1, and here is the intersection of A with B2, and then the intersection of A with B3 and so on. So each of these is the overlap between A and one of the B's. And since the B's don't overlap, then these pieces don't overlap. So in other words, these are disjoint pieces. So therefore, the probability of A is the probability of that, which is therefore by axiom 3, the probability of a union of disjoint events is the sum of the probabilities. So the probability of the union of AB1 and AB2 and so forth is the probability of AB1 plus the probability of AB2 and so on. Okay, now I'm just going to replace the probability of AB1 with the probability of B1 times the probability of A given B1. And I'll replace this by the probability of B2 times the probability of A given B2, and so on. Okay, now why did I replace that by that and that by that and so forth? Well, let's look at the probability of A given B1. The definition of conditional probability is it's the probability of the intersection of the events A and B1 divided by the probability of the event on which I'm conditioning B1. So if I take this formula right here and plug it in here, the probability of B1 cancels, and I'm left with the probability of the intersection, which is exactly this term here. So plugging the definition of conditional probability into here and canceling the denominator gives me that. Plugging the definition of conditional probability into here, canceling the denominator gives me that, and so forth. So in other words, this is a straightforward, simple-minded proof that this is a true statement. Okay, so it seems to me that the way to remember this, though, is to think about it in the frequency terms. And then the question is, okay, it's true. Now what you want to know is whether or not it's useful. So let me once more argue why this should be intuitively obvious, and this set theory analysis is really unimportant, unnecessary. What's the fraction of time that I get a point in A? Well, because I have a partition, I must either get a point in B1 or B2 or B3 and so forth. So this is the fraction of time I get a point in B1. That's the fraction of time I get a point in B2, and so on. Now, this multiplies the fraction of time I get a point in B1 by the fraction of time I get a point in A if I'm in B1. That's what conditional probability means. Same with this term. So obviously, if I add these up, I'm going to get totally the fraction of time I got a point in A, which was what I'm trying to show. Okay, so this is a correct statement. This is the law of total probability right here. So this is going to be very important because, as I'll show you in probability problems, it's often obvious that I can decompose a probability question into one involving a partition. So I'll give an example of that. That's the usual idea. So the example, let's see. Okay, here's an example I want to give. So I'm going to apply this. So before I do that, are there any questions now about this? Okay, so I'm going to apply this to an actual problem. And of course, the problem I'm going to apply it to originally is going to be one that's simple so that you know what's going on anyhow, so that you can then verify that what I'm saying makes sense. So here's the problem. I have an urn, typical probability model, and I'm going to have R red balls and W white balls. So I have R plus W balls in the urn, and I'm going to pull the balls out of the urn one at a time. And the question that I want to ask is, let me define RJ, capital RJ, being the event that I get a red ball on the jth try. So I'm going to pull the balls out of the urn one at a time, and I want to calculate the probability of red on the jth try. That's the question. Now, what is that? Well, first of all, let's calculate the probability of red on the first try. So that's kind of obvious. We've already done that one before. The probability of red on the first trial is equal to the ratio of the number of red balls to the total number of balls in the urn. Right? That was one of the problems that we did earlier when we first introduced this idea of sample spaces with equally likely events. And what I'm assuming here is that I'm sampling at random. So every time I reach in and pull out a ball, every ball is as likely to be pulled out as every other ball. Okay? Okay, so now the question is, what's the probability of red on the second trial? Anybody know? Well, the answer is I can't really answer the question yet because there's two possibilities here. How am I sampling? I could be sampling with replacement, meaning that I pull out a ball, I observe it, I put it back. I pull out a ball, I observe it, I put it back. I could be sampling without replacement. I pull out a ball, I keep it out of the urn. I pull out a ball, I keep it out of the urn. Now, if I'm sampling with replacement or without replacement, that's not going to matter on the first trial. But it may matter on the second trial. Because if I'm sampling with replacement, then the second trial is exactly the same, statistically speaking, as the first trial. Because the number of balls in the urn is the same. In fact, the second trial is independent of the first trial. Because we haven't defined technically what we mean by independence yet. We will. But it's sort of obvious from the meaning of the word. On the other hand, if I'm sampling without replacement, then the composition of the urn changes. Because I reach in, I pull out a ball, and whatever ball I pull out, the next time there's one less ball in the urn, and there's one less ball of the color that I just pulled out. So as I pull out the balls in the urn, if I sample with replacement, then these probabilities are going to be the same for every J. But if I sample without replacement, well, that's what we want to find out. And now I claim that if I sample without replacement, that this is the way to look at it. You'll see in a moment, it's obvious that this is the way to look at it. And so we'll compare sampling with replacement with sampling without replacement. Okay, so let me write down our rules here. A means with replacement. And B will be without replacement. Okay, so I'll underline out, without replacement. And now, let me denote these things by piece of A and piece of B. So the probability of red on the jth trial, any trial, I've done it for the first trial, but probability of red on the jth trial, if I'm sampling with replacement, is R over R plus W. Right? Because if I'm sampling with replacement, the first trial, the second trial, the third trial, they're all the same thing. Everybody buy that? That's straightforward. Okay, so now the question here is, suppose that I am sampling without replacement. So let me erase this and give myself more room here. So what I want to calculate now is the probability of red on the second trial if I'm sampling without replacement. Okay, so now I'm going to use the theorem of total probability, because I can say, well, it's obvious that the probabilities associated with the second trial depend on what happened on the first trial. In the first trial, I can look at that as a partition of my sample space, because on the first trial, I drew out either a red ball or a white ball. So the probability of red on the second trial, if I sample without replacement, is this. It's the probability of red on the first trial times the probability of red on the second trial given red on the first trial, plus the probability of white on the first trial times the probability of red on the second trial given white on the first trial. So the partition of my sample space is that on the first trial I got either a red or a white. That those events, the union of those events is the whole space, because that's all that can happen. Either I got a red or I got a white. And they are mutually exclusive or disjoint, because if I got a red, I did not get a white, and vice versa. So red and white on the first trial is a partition of the sample space. And it's sort of obvious that if I have this process evolving, that I should be able to represent the probability at any trial in terms of the probabilities of the trial in front of it. And so therefore, this idea of a partition of my sample space is a straightforward application. The first thing you would think of if someone said, okay, I'm going to pull the balls one out of the urn, sampling without replacement, and I want to find the probability that on the second trial that I get a red ball. Okay, so now let's just plug in the numbers here. What's the probability of red on the first trial? Well, we already know what that is. It's right here. Doesn't matter whether I'm sampling with replacement or not. That would be R over R plus W. What's the conditional probability of red on the second trial if I got red on the first? So now I have to apply conditional probability, but the question is this easy? Is this particular representation useful? And the answer is, well, sure, in questions like this it's obvious, because if I know that I pulled out a red ball on the first trial, then on the second trial, the answer is of the same form, except that the number of red balls in the urn is R minus 1, because I've already taken one out, and the total number of balls in the urn is R minus 1 plus W.
And then an R.
What was that?
R.
This is an R here. There is no N, unless you want to say that R plus W equals N. Sum of the fixed number of balls in the urn initially. Okay, now what about here? What's the probability of white on the first trial? Well, it's the number of whites, W, divided by the total number of balls in the urn. What's the probability of red on the second trial if I withdrew a white on the first trial? Well, the number of reds is still the same. The total number of balls in the urn is less by 1 because I drew a white out. So it would be R plus W minus 1. So that's my answer. I just multiply that out. Okay? So it's obvious, right? Straightforward how you're going to do this. Any questions? So let me test your intuition. Okay, so I can erase this. So the question I want to ask is, let me compare the probability of red on the second trial sampling with replacement, and I'm going to compare that with the probability of red on the second trial sampling without replacement. So which is bigger? So I got some possibilities here. You're more likely to get red on the second trial if I sample with replacement than without. So that's one possibility. Second possibility is it's the reverse. Third possibility is they're equal. Okay? Everybody buy this? Okay, how many people vote for greater than? 1, 2, 3, 4, 5. Okay, so you got 5 people voting for greater than. How many people vote for less than? 1, 2, 3. Looks like 3. How many people think they're equal? 1, 2. Okay, so we have a class of about 25 people here. Looks like we have 10 votes. Yes?
Wouldn't that depend on, like, if you had chosen a whiteboard first?
Well, that's the question.
Because if you had chosen a whiteboard first, then it probably would choose a red ball on the second one.
Yeah, if you choose a white ball first, that makes it more likely that you'll choose a red ball in the second one. But if you choose a red ball first, it makes it less likely that you'll choose a red ball in the second. So, which dominates? That's the question. Okay, so let me raise another possibility. Possibility is depends. Okay, because remember that you plug into this formula, you have the values of R and W. So it might depend on R, it might depend on W, it might depend on R plus W. In other words, you might guess that the answer should depend on how many balls there are of each type in the urn and not be always greater, always less, or always equal. I'm not saying it's true, I'm saying that that's a possibility, right? Which you didn't consider. So, considering the Monty Hall problem, I'll be Monty Hall here, so why don't I just give you another chance, right? So you pick another curtain. That seems fair.
But you didn't need it once, so you should be...
Okay, so what I'm doing now is I'm saying, okay, there's a possibility we didn't think of. Like previously, you didn't think of the idea that Monty Hall is always going to show you a goat no matter what, because he wants to maintain suspense. So I want to maintain suspense here. So what I'm going to do is I'm going to introduce this other possibility, which I think everybody agrees at least should be considered, and then ask you to re-vote. So you can change your vote or keep it. It's your choice. Okay, so now Monty Hall is getting this TV program going. So how many people now, recognizing that there's another possibility, think that greater than is the right answer? Okay, so we have 2. Are those 2 part of the original 5? Okay, so those people are solid. They're sticking with their guess. How many people think it's less than? 2, 3, 4, 5, 6. How many people think it's equal? 1, 2, 3. How many people think it depends on the values? Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the participation is going up, right? So this is now, 10 is now 10. Okay, so now we got 21 people voting. So that's pretty good. Okay, so let's answer the question. Okay, so here's the answer, because what I did here is I gave you a formula, but it doesn't really tell you much. So you could plug numbers in here, but so what? The purpose of all of this is really insights, not necessarily formulas for calculating things, because who's ever going to ask you this anyhow? Okay, so what I'm going to do is I'm going to factor out R over R plus W. So this is going to come outside, and then what I have here is this term, which is r minus 1 over r minus 1 plus w. And then over here, I factored out r over r plus w. So there's the r plus w, and there's the r. So what's left is that w, and the denominator is r plus w minus 1. Okay, now look at the thing in brackets. The denominator is the same for both terms. It's r plus w minus 1, r plus w minus 1. So they have a common denominator. The numerator is r plus w minus 1. So the thing in brackets has the value 1, no matter what the values of r and w are. So therefore, the answer is r over r plus w, which is exactly the same as what you would get if you sampled without replacement. So the answer is that. Okay? So almost everybody's intuition is way gone. Right? Any doubts? Yeah.
What if you only have one red ball?
Okay, suppose that there was one red ball and how many whites?
2.
Okay. Then this would be a 0, and this would be a 1. So that 0 plus 1 is 1, and I'd still have r over r plus w, which would be 1 over 1 plus w.
Because if you take away a ball, right? If that's without replacement, if you take away a ball, the probability of getting another ball on the second try is 0.
Of that color.
Right.
But how do you know you took away that ball?
That's it. That's without replacement. That's given that you took one out.
But yeah, it's given you took one out, but it's not given which one you took out. So if there were one red ball in the urn and you took it out, then of course it couldn't be the next, you couldn't pick a red ball on the second trial. But if you didn't take it out, then you're more likely to pick it on the second trial. So the point is that every time you pull a ball out of the urn, the probability that a ball of that color will appear on the next trial is less if the ball you pulled out was that color, and it's more if the ball you pulled out was a different color. So it's true that at any particular trial, the probability depends on what you did before, but what you did before, there are two possibilities. So you have to weight them. That's what this formula does. It says the fraction of time that I get a red on the first trial is that, and the fraction of time I get a white on the first trial is that. Now, if I got a red on the first trial, then the probability of a red on the second trial is smaller. But if I got a white on the first trial, the probability of red on the second trial is larger. And what the arithmetic shows is that they exactly compensate for each other. And it doesn't make any difference what the values of r and w are. This thing in brackets will always add up to 1. And that's the end of it.
But if you were looking for the third trial, then it would make a difference.
It wouldn't. Well, now I'm going to claim that what I've just proven is that the probability of red on the second trial under A is equal to the probability of red on the second trial under B. And we know that under A, the probability of red on the second trial is the same as it is on any trial. So this is what we already know. Now, the question is, suppose I look at the third trial. So is this equal to the probability of red, say, sampling without replacement on the J trial? Of course, now the answer seems to be obvious that it doesn't make any difference which trial you're talking about. Because once I'm at the third trial, it's just as if I was starting from the beginning with an urn with a different composition. So why should the second trial be any different from the third trial, the fourth trial? It seems to me obvious now that the following is true. The probability of red on the J trial sampling with replacement is equal to the probability of red on the J trial sampling without replacement, and that in every case is equal to R over R plus W, where R and W are the numbers of balls of each color in the urn at the start of the experiment. Go ahead.
If you were to add to that formula, right?
If what?
That formula that you counted. If you were to, right, the second from bottom. If you were to add to it the probability of, for the third trial, I was thinking that the first one kind of cancels out with the second one, but what cancels out with the third one?
Well, there wouldn't be another term here. What I would do is I would now, by induction, I could write the probability of red on the third trial is equal to the probability of red on the second times the probability of red on the third given red on the second. So I would use exactly the same kind of reasoning as before. And since we already know that the probability of red on the second is the same as the probability of red on the first, then it's exactly the same expression. Actually, there's more to this, because part of my argument is, let's see, what is my argument? First of all, I wanted to use the theorem of total probability and show that the theorem of total probability is useful. So you can see that lots of probability problems might have the format that you have something that happens in some kind of sequence, and then it's easy to see what the partition is, and then it's easy to see what the conditional probabilities are, and then you just have to put them in a formula. So I picked a particular case in which it's obvious that the theorem of total probability applies. Then we wrote it out, and then made the observation that surprisingly, okay, obviously it's a surprise, that surprisingly, at least at first glance surprisingly, that the probability of red, and the same also with white, the probability describing what happens on the second trial is the same as the probabilities for the first trial, whether or not I'm sampling with replacement, whether it's replacement or without replacement. So that seems rather surprising. But then that raises an issue, because if it's true that the probability of red on any trial does not depend on whether I sample with or without replacement, and is this simple? Remember, this is like if you knew nothing at all about the subject and somebody asked you to guess what this probability is, I think the most reasonable guess is the ratio of the number of balls of any particular color to the total number of balls. So the question is, why did it work out this way? Was it just a coincidence of algebra that things happen to cancel out? And of course, coincidences don't happen. So if it just happened, if it happened that things canceled out, there's a reason for it, which means that maybe there's a more direct argument, or maybe a more indirect argument, but a more insightful argument. Because you'd like to know why this is true, whether this is just a bizarre quirk of fate, or whether or not, if I looked at it a different way, I'd say, of course, it has to be that way. Okay, so let me make some calculations using different arguments. Okay, so the first argument is this. Okay, I'm going to calculate the probability of red on the jth trial under sampling without replacement. Because sampling with replacement, there's no question. Everybody agrees that since the composition of the urn doesn't change, if I sample with replacement, then that's the answer. Okay, so it's only the sampling without replacement that we care about. So now I'm just going to look at it this way. I'll say, okay, I have this urn. I'm sampling without replacement. So what I'm going to do is I'm going to take the first ball and put it in position 1, and the second ball and put it in position 2, and so forth. So I'm reaching in, I'm pulling out the balls one at a time. There's position number J, and then finally there's position R plus W. Okay, now we want to find the probability that we have a red ball in position number J. So I have this urn, and the urn has I'll call red ball number 1, and it has red ball number 2, and so forth. And it has white ball number 1 and white ball number 2, and so forth. In other words, the balls are physically distinct. They know who they are. So imagine each one has a number on it, or a tattoo or something. And now you say, okay, what's the probability that this position is occupied by a red ball? Well, the probability that this position is occupied by a red ball is the probability that either it's occupied by the first red ball, or the second red ball, or the third red ball, and so forth. Now, the probability that red ball number 1 happens to lie here is 1 over r plus w. Because if the balls are selected at random, then every ball is as likely as every other ball to occupy every position. So the probability that a particular red ball occupies a particular position is 1, because there's one such red ball, divided by r plus w, the total number of positions. Okay, now let's go to the next red ball. What's the probability that it occupies that position? Well, it has the same probability, and those events are mutually exclusive. Because if red ball number 1 is here, then red ball number 2 has to be someplace else, and vice versa. So, probability that that position number j is occupied by red ball number 1 is 1 over r plus w. And the probability it's occupied by red ball number 2 is 1 over r plus w, and so on. Now, how many such terms are there? Well, there are r red balls. So when I add those up, I'm going to get r over r plus w, which of course is exactly the answer we know is right. But now I did it without any arithmetic. Now you can see exactly why it works. Okay? I have this urn. I'm sampling without replacement. So what I'm going to do is I'm going to ask for the probability that if I take the balls and I put them in a line, here's position 1, position 2, and so forth, and there are r plus w positions, I want to know the probability that any particular position is occupied by a red ball. The probability of that is the probability that it's occupied by the red ball that we'll call Frank, plus the probability it's occupied by the red ball that we'll call Mary, and so forth. So each of those probabilities is 1 over r plus w, because Frank is one red ball, and he has equally likely to occupy any one of r plus w positions. So the red ball called Frank has this probability of occupying that position. The red ball called Mary has that same probability of occupying that position, and so on. And since those events are mutually exclusive, if Frank is here, Mary has to be someplace else, that means that the probability of the union is the sum of the probabilities. So I just add up r probabilities, where each one of them is 1 over r plus w. So that's the answer. So that shows you that it works not only for position number 2, it works for all the positions. It doesn't make any difference. Is that a question there? All right, let me give you another argument. Here's the argument that you would have used in the first part of the course when we were just talking about sampling sample spaces with equally likely outcomes. So now I'm going to take a different viewpoint. So here's the probability of red on the, let's see, let me make it the second trial, because I've already done it in general, and I don't want to confuse the issue. I just want to show that if I make this calculation for the second trial, I get exactly the same answer, no matter how I do it. So here, now instead of taking the balls one at a time and putting them in a row, say, now I'm going to reach in and I'm going to pull them out all at one time, and then after I get the balls as a group, then I'm going to put them in order. So if I do that, the first thing is, how many subsets of size 2, because I'm reaching in, I'm talking about the second one. So what I'm going to do is I'm going to reach in, I'm going to pull out 2 balls, and then I'm going to call one of them the first and one of them the second. So how many ways can I pull out 2 different balls? And the answer is, well, there are r plus w balls, and I want to pull out 2 of them. So that's the total number of selections or sets of size 2 that I can make by reaching and just pulling out 2 out of the r plus w. Now in the numerator, I want to count how many of these choices have the property that a red ball is the second one I draw out. So one possibility is that from the red balls, I draw out 2, and from the white balls I draw out 0. And if that happens, then it must be true that the ball that I call the second one is red. The other possibility is that from the red balls I draw out 1, from the white balls I draw out 1, but then I have to multiply by 1/2, because if I draw out 1 red and 1 white, half the time it'll be red-white, half the time it'll be white-red. So I multiply this by 1/2. Now, it's just algebra to actually work this out. It's very easy. In fact, I guess I'll do it. R choose 2 is R times R minus 1 over 2. W choose 0 is 1. Here I have R choose 1 is R. And W choose 1 is W. And there's the 2. And the denominator, R plus W choose 2 is R plus W times R plus W minus 1 divided by 2. The 2's cancel. And now I can rewrite the numerator just like that, and everything's going to cancel, and I'm going to be left with this. Okay, so take my word for it, if you don't see it there, that if you work this out by algebra, it'll turn out to be exactly that. So this is not very enlightening, because it's the same as this. It looks like the reason that the answer turns out to be this is just a trick, or just a coincidence. But this is just another completely different argument that gives me exactly the same answer. Okay, so this is looking at it the way we look at the poker problems. Okay, any questions about that? Everybody believe that now? So you got to digest that. What it says is that at each trial, the probability, if I'm sampling without replacement, at each trial, the probability of getting either color depends on the composition of the urn at that time. And as I sample, the composition of the urn changes. But the changes compensate for each other, because every time I pull out a ball of one color, that lessens the probability that I'll pull out a ball of the same color the next time, and vice versa. Yeah.
So this is talking about the overall probability before the experiment is ever done, because it's going to change slightly as.
Right. At each time, if you know what's happened before, then you know the probability of happening at that time. But if the question is, I'm going to pull out these balls one at a time, and I want to know the probability the 10th one is red, then it's just equal to the ratio of the original number of reds to the total number of balls in the urn. In fact, it's just like the question with poker, or with a deck of cards. I have this deck of cards, I shuffle them, and I ask, what's the probability that the first card is the ace of spades? Well, 1 over 52. Suppose I say, what's the probability the 14th card is the ace of spades? Well, it's 1 over 52, because the ace of spades is just as likely to occupy one position as any other. But people, at first glance, say, wait a minute, I can't tell you what the probability is that it's the 14th card, because maybe it's one of the first 13. And if it's one of the first 13, it can't be the 14th. That's true. But maybe it isn't one of the first 13. And if it isn't, then it's more likely to be in the 14th, because you've already eliminated 13 cards, and the ace of spades wasn't among them. So they balance. So this is one of the intuitive things that you have to digest. Okay, so let's go back to the Monty Hall problem and see if I can use the theorem of total probability to convince you that the Monty Hall problem is as I said. Okay, so now I'm going to formulate things differently. So here's Monty Hall again. So now I'm going to have two strategies. The contestant can either adopt a strategy that says, I'm always going to switch, I'm never going to switch. Those are his two possibilities, two strategies, and what you want to do is you want to calculate the probability of winning with one strategy versus the other. Okay, so here's strategy one. So strategy one is to stay with first choice curtain. So let's call the probability of winning with strategy 1 P1. Okay, so the strategy is that whatever the contestant picks, that's it, he sticks with it. So let me call that PC1. I'm introducing some notation now. So C1 means that he stays with curtain number 1. So his winning, probability of winning, what this means is car under curtain 1. And that probability is 1/3, because when the contestant originally picks, there are 3 curtains, there's 1 car. The chance that the contestant will pick the right curtain is 1 chance out of 3. Here's strategy 2. This is switch from first choice curtain to the remaining curtain. Okay, so now I'm going to use the theorem of total probability to figure out what's going on here. So the probability P2, that's the probability of winning if I adopt strategy number 2. And that's the same thing as saying, what's the probability that a car will be under the second curtain selected? And now I'm going to apply the theorem of total probability. Total probability. Theorem of. Okay, so what's the probability that there's a car under the second curtain that the customer or that the candidate selects, contestant selects, given that he's going to switch from the first choice? Well, PC1 is the probability that the first curtain selected contains the car. So he will win if the second curtain contains a car, given that the first one contained the car. Then I have the probability that the first curtain contains a goat, and I multiply that by the probability that the second curtain will contain a car, given that the first curtain contained a goat. Okay, so this is just a formal application of this theorem of total probability, because we're asking, what's the probability that the second curtain contains a car? So we're saying that we have a partition of the sample space. Either the first curtain contained a car, or the first curtain contained a goat. Multiply the probability that the first curtain contained a car by the probability that if the first curtain contained a car, the second one contains a car. And multiply this by the probability that if the first curtain contained a goat, then the second curtain contained a car. So this is just a formal application of the theorem of total probability. Okay, so what are these? What's the probability that the first curtain hides a car? And as we all agree, that probability is 1/3. What's the probability that if the first curtain hid the car, then the second curtain will hide the car? 0. Can't happen. What's the probability that the first curtain will hide a goat? 2/3, because there are 2 goats. So when the contestant picks a curtain, the chances are 2 out of 3 that his initial guess will be a goat. Okay, now we have to multiply that by the probability that the second curtain contains a car if the first curtain contained a goat. Okay, so this is the critical one right here.
Just after Monty already pulled up the curtain.
Well, yeah, that at this point now, there's two possibilities. One is that Monty always shows you a car, and the other is that Monty shows you a car by chance. Okay, if Monty always shows a goat, if Monty always shows you a goat, then what that means is that given that the contestant chose a goat originally, since Monty will never show you a car, Monty will always choose the other goat, then the probability that the remaining curtain has the car is 1, and so the answer would be 2/3 times 1. So this probability is 1 if Monty always shows goat. Okay, now I don't have room to write here. Maybe I should make myself have room. What would this probability be if Monty happens to show you a goat? Well, if Monty chooses by chance, then if the contestant has already removed the goat, the probability that Monty will then pick a goat instead of a car is 1/2. But 1/2 is not always. Let's see, 1/2 is by chance. So if Monty shows it by chance, then it's 1/2 times 2/3, which of course is 1/3. Okay, so what that means is that if Monty always shows you the goat, then this probability is 1, and the probability that the contestant will win if he always plays strategy 2 is going to be 2/3 times 1, which is 2/3. On the other hand, if it turns out that Monty shows you the goat by chance, then this probability is 1/2. That means that if the contestant always plays strategy 2, the probability that he will win by switching will be 1/3, which is exactly what he would get if he didn't switch, 1/3, which means that if he switches, then he doubles his chance, going from 1/3 to 2/3, if Monty always shows a goat. And if Monty shows a goat by chance, then if he switches, his probability goes from 1/3 to 1/3 or stays the same.
So it all depends on what you hold, the selector.
It all depends on Monty, of course. If we agree that Monty always shows you a goat, then the contestant's best strategy is to switch, because if he switches, his probability of winning will be 2/3.
So then in all this reality, that's not a true strategy.
Well, no, it is in reality. You could argue because if on the game show, Monty is always going to show you a goat because he wants to maximize the suspense, in that case, the contestant doubles his chances of winning from 1/3 to 2/3 by switching. So if Monty just happened to show you the goat by chance, switching doesn't make any difference. And if he shows you the goat on purpose, switching doubles your chances of winning.
So you're betting that Monty wants to maintain suspense. So
I'm not betting that Monty knows what he's doing, although I'm assuming that. Okay, I'm saying that from one point of view it doesn't matter, because if I switch and Monty shows me the goat on purpose, then I double my chances of winning, and if he shows me the goat by chance, it doesn't make any difference, so therefore I should switch. The other point is that most people don't realize that, until this is pointed out to you, that the fact that Monty shows you the goat by itself is not enough information. What you need to know is, did Monty show you the goat on purpose, or did Monty show you the goat by chance? So the reason for Monty showing you the goat affects the probability, not just the fact of whether he showed you the goat or not. So therefore, this is, for most people, very disconcerting. As I say, according to what I read you, this generated thousands of letters from outraged mathematicians and other people who thought they knew what they were talking about because they didn't really think about it, because they didn't give Marilyn any credit, I guess, or maybe she wasn't clear in her statement of the problem, which she might have done on purpose, which is really quite reasonable. Because remember, in real life, if you're a scientist or engineer and you're applying probability, that doesn't mean that somebody asks you a question in a textbook, which everything is specifically, clearly written out. It's very vague. What's the probability that if I design a system this way and shoot this thing into orbit that it's going to explode? Well, who's to say what all the parameters are? Does it matter whether there's temperature? Does it matter where the sun is? Does it matter whether it's raining or not? Does it matter when your birthday is? I mean, those are things that the analyst has to bring in on his own, and what you put in and what you put out, that's part of the model. There's no real answer for that. So this subject involves two tricky elements. One is making the right model, and then the other is drawing the right conclusion once the model is made. So it's tricky. Yeah?
I need to ask you a question. I mean, is it okay to assume that Monty is always going to show you a code, or he could be bluffing, I guess?
Right, well that's his question. And what I'm saying is, if you assume that Monty always shows you a goat, then it's better to switch. If you don't assume that Monty always shows you a goat, or whether you assume it or not, if Monty does not always show you the goat, but picks by chance, then it doesn't matter whether you switch or not. If you're interested, what you should do is send me an email asking me for the websites, and then I will send back this list of websites, and then you can go and read. They all have links to other things. You could spend your whole life reading about Monty Hall. Are you convinced now?
Yeah, finally.
Okay, that was my goal. You always have to convince the skeptics. That's the goal of any preacher, right? Okay, let me give another example. This one's in the book. Find it here. The example I want to give is the gambler's ruin problem. And the reason I want to give this example, remember this example, we didn't need this analysis. This example we could have done other ways, but using the theorem of total probability was the most direct way to do it. It was the most obvious. So now I want to give an example where the theorem of total probability applies, and it's hard to see some other way of doing it. So this is the gambler's ruin problem. And this is in the book. This is example 3.14, page 90. And the basic idea is this. You have this gambler, and he has a certain amount of money. He has $8. I think it's A. Let me make sure I'm using the correct terminology here. Yeah. Okay, he has $8 and he plays this game. And the game is that he tosses a coin. And let's say the coin is a biased coin, heads or tails. And if he gets a head, he wins $1, and that probability is P. And if he gets a tail, he loses $1, and that probability is Q. So P plus Q adds up to 1. If it's a fair coin, then P and Q are equal, it's 50-50. But it doesn't have to be. So he tosses a coin, and with probability P, he wins $1, and then he tosses it again. With probability P, he wins another $1, and he tosses it again. With probability Q, he loses $1, and so forth. And the question is, what's the probability that he will get ruined? Now, I don't know why they ask it in that negative fashion, but let's look at it like this. He starts off with $8, and he's going to play until either he has A plus B dollars, that is, he wins B dollars, or he gets ruined, he goes broke. So if you look at an individual player on an individual set of trials, what's going to happen is this. He starts out with A, and then he might win, lose, win, and so forth. And he's going to bop around in here, and eventually he's either going to come up to here, at which time he quits and he wins B dollars, or he can bop around and eventually come down to here, in which case he's broke and he winds up losing A dollars. And so the question is, if he starts out with A dollars and he plays until either he gets ruined or he wins B dollars, what's the probability that he will get ruined? That's the way the problem is stated. And the idea is that at each trial, he has a probability P of winning $1 and Q of losing $1. Okay, so the simple version is where P and Q are 1/2. Now you could say, okay, how can I analyze this? Well, first of all, notice that if I look at every possible path, because he starts out here, and there are two possibilities for the end of the game. Either, well actually there's three. One is that either he gets to here first, or he gets to here first, or another possibility is that he oscillates forever and he never reaches either of the two boundaries. But however you look at it, you can see that there's an infinite number of paths in the sample space, because I could start from here and I could win directly, or I could lose, and then there's every other variation of this. So since there's no necessary number of trials that are going to lead to the game ending, there's an infinite number of paths. Now, the probability that he is ruined is going to be equal to the sum of the probabilities associated with each path that ends at the bottom. And the probability that he ultimately wins is the sum of the probabilities associated with each path that ends at the top. So you have to add up the probabilities of each of those paths. Now, obviously, the paths don't have equal probabilities. In fact, they can't, because if I had an infinite number of possibilities and they were all equally likely, and they had to add up to 1, that's impossible, because you can't add up an infinite number of positive values that's going to add up to a positive value. It's going to diverge. It's going to go to infinity. So that means that each path has a different probability. Obviously, the longer paths have smaller probabilities. And so if I were to try and calculate this by calculating the probability associated with each path and adding them up, this would be a horrendous problem. Because first of all, I've got an infinite number of possible paths, and second of all, they all have different probabilities. And they're very complicated, because remember, in any particular path, you go up and down, one step at a time. So the combinatorics involved in that is mind-boggling. Nevertheless, it seems to be a simple problem. So let me first show how the theorem of total probability applies in general, and then ask a simple question. Actually, I'll ask the question first because it's worth thinking about. And then I'll show how to solve it next time, because I don't have much time left. Let's suppose that this gambler starts out with A, and he's going to play until he either goes broke or gets A plus B. And let's say that P equals Q equals 1/2. Let's make it simple. So in other words, he's tossing a fair coin. And let's say that A is $1 million. So this is a rich guy. He goes to this. He goes to Monte Carlo. He's got $1 million to spend. He's going to gamble $1 at a time, and he's going to gamble until either he makes $10,000 or he goes broke. And his argument is, okay, $10,000 isn't that much. If I make $10,000, that pays for my vacation. I go home, I get a free vacation. So the question is, what's the probability that he gets a free vacation? Vacation, V-A-C-A-T-I-O-N. What's the probability that he gets a free vacation if he starts off with $1 million and plays until either he gets 10,000 or he goes broke? So let me give three. Let's have a little scale here. Okay, here is 10%. Here's 50%. Here's make this 90% right here. So this is a 10. So yeah, This is 90%. So in other words, if the gambler goes to Monte Carlo, he has $1 million, he's willing to risk, he's going to play until he makes $10,000 or loses. What's the probability that he will in fact get a free vacation? That he'll win his $10,000 before he goes broke? How many people think it's less than 10%? How many people think it's between 10 and 50? Wait. How many people think his chances of winning before he goes broke is less than 10%? Let's say 3. How many people think it's between 10% and 50%? Let's say 5. I'm estimating here, roughly. How many think it's between 50 and 90? 2, 3. How many people think it's between 90 and 100? Nobody. Okay. Once again, we have a lot of slackers here. Full vote. Okay, next time I'm going to analyze this problem using the theorem of total probability, and then I'll show you what the answer is. Of course, the answer is exactly the opposite of what everybody thinks. Any questions before we quit? People in Port St. Lucie, we got 1 minute and 20 seconds. Okay.